Hello everyone, my name is Kurt Schilling from Vanderbilt University, and today I will be presenting our paper from the upcoming issue of MRM entitled Functional Tractography of White Matter by High Angular Resolution Functional Correlation Imaging, or HARFI. So I'm going to start with describing this method that we've called HARFI that we use to evaluate resting state bold signal changes, specifically in white matter. I'll discuss some of the motivation, some potential applications, and how we can maybe use this to bridge the gap between structural and functional connectivity. So starting with this picture, this may look a lot like the diffusion MRI glyphs that we've seen for a couple decades, where these renderings point in the direction that we expect or that we think neuron or axon fibers point. But these figures were not made with diffusion MRI. This is actually created using only bold contrast, typical of functional MRI studies. To date, most functional MRI has focused on brain gray matter. However, there have been several reports of task-based functional activations in white matter regions, such as the corpus callosum, the internal capsule, and the optic radiations. And the motivation for the current work actually comes from a study from Xiaohua Ding and John Gore here at Vanderbilt, where they actually look at neighborhood correlations of signals and discover that there's a distinct anisotropy in many regions. And these regions were largely consistent with the orientation that we expect white matter pathways to follow. These correlations actually extended over large distances, as much as 10 millimeters or more. And Xiaohua characterized these correlations using what he called the functional correlation tensor in direct analogy to the diffusion tensor, which is often used to characterize diffusion MRI. So in diffusion MRI in the early 2000s, researchers and groups realized limitations of diffusion tensor for capturing these, orientation of fibers. And they quickly moved to what's called high angular resolution diffusion imaging, or HARDI, which allowed much more complex representations of, in this case, the structural geometry, where they attempt to capture the fiber orientation distribution. So in the same way that HARDI improved upon the diffusion tensor, this work takes the functional tensor and attempts to capture a high angular resolution functional imaging metric that we refer to as the functional orientation distribution. So some of the limitations of the functional tensor were that it used only nearest neighbor voxels, which made the functional tensor sensitive to noise. Second, adjacent neighboring voxels tended to have higher correlations than their diagonal neighbors, possibly caused by decreased distance from the voxel of interest, which could cause orientation-related biases. Third, the use of a second-order tensor limited the shape of these functional distributions to ellipsoids. And finally, it also forced a symmetry, bipolar symmetry, which is left over from diffusion literature, where we're unable to distinguish diffusion in the left direction from that in the right. So to overcome these, HARFI utilizes a large neighborhood because we know these correlations extend over large distances. We implement a uniform angular and radial sampling of correlation functions, and we actually allow the functional distribution to take any shape or any function over a sphere. So starting with some of our methods, we perform a very typical single-shot T2 star-weighted gradient echo EPI on a 3T scanner for 16 subjects. We pre-process with slice timing, head motion, move to MNI space, and detrend and low-pass filter the data, followed by normalization to unit variance. In the original functional tensor implementation, the correlation tensor T is computed from the correlation coefficient of all neighborhood voxels, all 26 voxels, and T can be represented using ellipsoidal contours, much like the diffusion tensor. In the HARFI implementation, we actually sample not just neighborhoods, the neighboring voxels, but actually concentric spheres of the neighborhood, asking what the correlation coefficient is in every direction across a radial distance. We then integrate that radial distance for every direction, resulting in our HARFI function, f. We then fit this function to spherical harmonic coefficients, much like we do in diffusion imaging. One unique aspect of HARFI is that we can actually fit the function to a full complement of spherical harmonic coefficients, as opposed to diffusion literature where you would only fit to the even order coefficients. So in this case, we fit to even and odd orders, which allows asymmetric distributions. We can then calculate measures of asymmetry of these HARFI functions. For example, calculating the degree of bending, the degree of fanning, the number of unique peaks, the asymmetric power, which is just the ratio of the asymmetric coefficients to the total complement of spherical harmonic coefficients, as well as the homogeneity index, which describes how similar an individual voxel is to its neighbors. So moving on to HARFI results, we can actually calculate this HARFI function in every voxel in both white and gray matter and visualize many of these glyphs in the same way and actually using the same software that we would for diffusion. We show that we're able to capture complex functional orientation distributions. For example, in regions where we'd expect crossing fibers structurally, we get a crossing functional distribution, here showing 4 distinct peaks. We can also get even more complex regions where there are ultimately 5 or more unique peaks in this function. We then asked whether we could use these functional orientation distributions to perform fiber tracking. And we were very happy to find that we were indeed able to track several major pathways using just bold contrast, resulting in pathways that were very similar in size, shape, and orientation to those that we might get using diffusion MRI. We were also able to find regions of asymmetric functional distributions. These 2 figures show places where there's a very clear fanning of functional orientation, where one lobe of the FOD is smaller and the other is much more expansive. We also saw very unique functional distributions. For example, 3-way crossings, which may be indicative of 3 pathways coming together, as well as very distinct U-shaped functional distributions where we know that superficial U fibers exist along the sulcal fundi. We can also look at several asymmetric measures. Here we're looking at the average T1 over all of our subjects, as well as the measures described earlier. The asymmetric power, we see large asymmetry in many of the regions that we were able to see qualitatively. For example, U fibers, or places where we expect crossing or fanning fibers. The homogeneity of these FODs is generally less homogeneous in the white matter, where it may be intuitive to think that these measures change spatially. We also can examine the number of peaks, the bending angle, which again shows large angular bending, maybe where we'd expect U fibers to curve sharply, as well as fanning index, which is unique because this indicates that a lot of the fanning may be happening at the white matter-gray matter interface or in the cortex itself. So we've shown that using the anisotropic correlations of the bold signal, we can characterize complex functional orientation distributions. And these distributions can actually be used to perform functional tractography. While the ultimate significance and potential applications of HARFI remain to be established, it's already clear that these resting state signals in white matter represent some level of neural activity that has been largely ignored, and which represent functional variations that may be closely coupled with the corresponding activities in the cortical regions to which they connect. Because of this, HARFI tractography provides a unique and novel way to potentially identify functional connectivity. And the ability to detect and quantify correlated functional signals in white matter is a crucial aspect of delineating functional circuits in the brain that is currently unavailable from other functional MRI methods. So it's natural to expect some geometric relationship between the functional and structural connectivities in the brain. There's potential to use these techniques or similar techniques in order to harmonize diffusion MRI structural data and functional MRI functional data. We envision using the asymmetric HARFI distributions to possibly improve fiber tracking specificity and sensitivity. For example, it's currently not possible to distinguish diffusion processes in one direction from diffusion in the opposite direction, which may lead to ambiguity in estimating the fiber geometries in each voxel. And we've shown that using HARFI, we can actually characterize very unique fanning, bending, and even three-way asymmetric crossings. This ambiguity in diffusion data can lead to both false positives and false negatives in tractography. So some potential interesting future work could potentially develop an appropriate tracking strategy that uses these asymmetric HARFI distributions in order to evaluate the sensitivity and specificity of the resulting tractography. So to wrap up, we've presented a new way to evaluate anisotropic bold signal changes in white matter, capable of characterizing complex functional distributions, and also capable of characterizing what may be called functional pathways. These techniques could possibly be used to bridge the gap between structure and function in the brain. And future work should investigate modulation of these pathways during functional loading, or quantify temporal modulation in resting state conditions. We've briefly explored this and we'll be presenting our work at ISMRM this year, where we look at the difference, or really directional differences, in HARFI signals when we compare two different loading conditions. And we found very unique, not only very unique spatial patterns, but very unique directional patterns. With that, I'd like to thank Vanderbilt University Institute of Imaging Science, the Massey Lab, and of course my funding sources. Thank you.